So welcome everyone to the Canada Wildfire webinar. Today is October 13th, Friday the 13th, and we have Dr. Laura Chasmer here talking to us about her awesome field season that they had in their lab. Before we begin, I would like to acknowledge that Canada Wildfire is located on Treaty 6 territory, and we respect the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada. I am located in Leduc, Alberta, also on Treaty 6 territory. So I'd like us all to take a moment to think about the place we live and who may have lived here before and care for the land. Okay, so as I said, today we have Dr. Laura Chasmer from the University of Lethbridge here. She's going to be talking to us about her Epic Adventure 2023 and the field season that they had. Before we begin, I would like you all to know that Laura will be posing a few questions throughout her presentation. So please feel free to answer the questions in the chat box. We'll also use the chat box to put in any questions that arise from you throughout the presentation. And at the end, we'll have a live Q&A where I will ask those questions to Laura. So with that, I'm going to hand over the reins to Dr. Laura Chasmer.
Thanks very much, Karen. I'm very happy to be here. Today, I'm going to be presenting on our Epic Adventure from 2023. So within this adventure, we go through and we measure fuels. We fly lidar, RPAS, or remotely piloted aircraft systems. And we collect photogrammetric data at sites across Canada. But before I start, I would like to recognize that the University of Lethbridge is on Blackfoot territory, and we recognize and appreciate the history that the Blackfoot culture have brought to the university and to the land, and of course, all First Nations people living in Canada. I would also like to acknowledge the many people who've worked on this project with me, and for which I really couldn't have done this work without them. Emily Jones, Maxim Okremenko, Chris Hopkinson, Tristan Skretting, Jojin Ji, Saeed Parsian. We do a lot of work with Hatfield Consultants, which are fantastic to work with. Patrick James at the University of Toronto, Jonathan Boucher, and Guillermo Castilla at Canadian Forest Service, Chris Watson at Parks Canada, and of course, Rafael Chevardez, who is also at Canadian Forest Service. So when I put this together, I was thinking of our adventure as being epic. And it's more like, you know, epic in the sense that kids would use the term like, that was epic, man, kind of an epic story. But it kind of got me thinking, you know, what is an epic story or poem in reality? And what does it include? So before I start, I wanted to ask people in the audience, you know, what constitutes an epic story? What makes something epic? And if you can put it in the chat, I'd really like to know what you think is an epic story. So before we, oh, it seems to be advancing without me knowing. So before we start, if anyone knows what an epic story, that would be great. Basically, if you're, you know, if you're knowledgeable in English literature, an epic story typically includes a hero. It includes an adventure where the hero is put into a position of peril or disaster. And of course, you know, being an academic, you hope going into the field that you don't end up going through an epic adventure. You want everything to be pretty mundane, but we did have a little bit of epic kind of things happen to us while we were in the field, which I'll talk a little bit about. Okay. So, of course, in Wildfire, there are many, many modern epic adventures, and we have lots of heroes in Wildland Fire, and my group we're nowhere even close to being on that kind of role. We had a little tiny epic adventure compared to most wildland firefighters, but I just wanted to show you kind of some of these epic situations that have occurred. The right is a photograph that I think I've grabbed from somebody, probably from the media. I can't quite remember. I apologize where I received that. But you see all of these people kind of lining up in their cars with the peril of fire around them. And this is a very real situation here in Canada as people are evacuated from these fires. On the left, there's a photograph by Joël Voglemachi at the University of Montreal. And here you can see the Scotty Creek wildfire approaching the watershed. And this is the last photo that was taken before the students were kind of left that area. And of course, this whole area burned down. I'm going to talk a little bit about that. So the problem here is that vegetation structures and fuels are changing. And so they're having a big impact on our understanding of fire behavior. And this is something that is well known. The other issue is that in order to understand how fires are changing, we need to put in a lot of plot measurements and to understand those structures and to figure out how fire is behaving in the landscape. So if you've ever measured plots, forest plots, they're very costly to install. They can be really time consuming to measure, and you really can't put in enough of them to characterize the full diversity of Canadian forests. So we need to find some other way of measuring these structures within the landscape. Just to provide an example, I've got two photographs that were taken by Tristan Scratting here at the University of Lethbridge. And Tristan's a master's student working with me. And on the left side, you can see a north-facing slope in the Lynham Valley at Waterton. And you can see there's a person there kind of measuring the trees. And this was really a difficult area to measure because it was so steep. But the trees have lots and lots of fuels within them, lots of ladder fuels here that the fire can kind of climb up. All of these fuels are very dry. And the mosses in this forest are really thick and deep. On the right side is the south-facing slope. And the forest structures are very different. Now, these forests are only maybe about probably about 500 meters to a kilometer away from each other. And they're at the same elevation. And yet the forests are so different just because of the kind of the energy balance within that system and how those forests have grown. So here's another example of a rapidly changing landscape. And this is a peatland from the Scotty Creek watershed before it burned. And in fact, it's the same peatland as what's shown in the photograph below as the fire is approaching. This peatland, you can see here, lots of mosses. This is kind of a wet area or historically wet area with trees that are growing on permafrost plateaus. And so as the permafrost is thawing, the trees are starting to fall over and they're starting to die, which creates additional fuel. In addition to that, these mosses are starting to dry out because of the warming, drying conditions in the north. And so this contributes to even more fuels within the landscape. So one solution that my group and lots of other folks have been working on is to use airborne lidar systems. So lidar is a technology, it's basically a ranging technology, and I'm sure most of you are familiar with it. But it's quite a simple system. It shoots out laser pulses in a kind of a sawtooth pattern as the lasers swept back and forth out of the bottom of the airplane. And the system basically measures the timing of the laser pulse emission and laser pulse reflection. So then you combine that with an inertial measurement unit within the airplane and a kinematic GNSS. And what that does is it measures basically the location in X, Y, and Z of the laser pulse reflection as it is intersected by biomass in tree canopies, but also the ground surface. So I've kind of pasted a whole bunch of dots on these trees here showing what LiDAR data looks like. But in fact, LiDAR data or LiDAR systems can penetrate right through the tree canopy all the way to the ground surface, which makes it highly beneficial for looking at fuel structures and vegetation structures more generally. The other thing about LiDAR is that it's not often occluded by or shadowed by vegetation kind of overlapping each other. So, which is a problem with optical remote sensing. So you really can kind of penetrate down to some of the really important components of the forest that are important for understanding fire behavior, such as, you know, the understory, the downwoody debris, and the ladder fuels. So LiDAR provides us with a relatively dense three-dimensional point cloud of the vegetation structure. Now, we can get even higher density data by using drone-based LiDAR systems, which you can see here on the right. And these basically scatter points, you know, every few centimeters within the canopy. So you really can get very highly detailed kind of components of that canopy and the understory. So we had a plan to measure and map fuels across Western Canada, and it really was kind of the adventure of a lifetime, I would say. We basically started all the way down in Lethbridge here, and we drove up. Some of us flew up to Yellowknife. We went over to Scotty Creek and Fort Simpson in the Northwest Territories, drove across to Watson Lake, measured fuels there, went all the way down to Jasper and Banff, and then back over to Waterton. And I apologize, my labels seem to be in the wrong spot there. So we put plots into all of these different areas. We traveled more than 8,000 kilometers, and these routes do not actually represent the highways we took very well, but needless to say, we kind of got to all those places. We also got to other places where we didn't measure, such as Tomahawk area, where there was a fire this spring just outside of Edmonton. We flew parts of the Uticuma Regional Study Area, which is really interesting because it burned in 1956. Part of it burned again in 2011, and part of that burned again this year. So we've got kind of a decreasing return intervals in fire. And then we also flew up to Lutos and collected LiDAR data around there. So these sites in red are the areas where we didn't get field data, but we got LiDAR data. So we've been putting fuel plots in since about 2020, when Canadian Forest Service first came out with their next generation Canadian Forest Fire Danger Rating System methodology for putting fuel plots in. And before that, we've been putting forest mensuration plots in since 2002. So we've been doing this for quite a while, and we've collected really quite a nice set of coincident LiDAR and forestry plots. So this year we had a really great team of people joining us, and this was the whole team. So we didn't have all of these people all the time, but they joined us. All of these folks joined us in Jasper. But we started off with myself and Chris Hopkinson, Italo, Emily, and Jen and Amanda in the north, measuring those plots. And then Natalie and Jessica joined us kind of in the national parks. Natalie is an undergraduate student. Jessica is just started her master's, as has Amanda. And Jen is an internship student who visited us from France. So for Jen, it was quite an experience. She's from Paris and she'd never really done the remote work, in the past, but we've managed to take her out and show her all these great forests. So we also had an airborne team, and the airborne team included Maxim Okremenko, who is our lidar operator, and he's a PhD student with Chris Hopkinson, and a great pilot from Aries Aviation out of Calgary, who I can't remember the name of. So there you go. This is our system here down on the left-hand side. So we fly an airborne Titan multispectral LiDAR, which is produced by Teledyne Optech. And it's a few years old now, but there are only about, I think, 4 LiDAR systems like this in the world. It's unique because it emits pulses in 3 wavelengths, green, near infrared, and shortwave infrared. So it's particularly good at measuring vegetation structural characteristics using the near infrared, but also moisture and the basically blackened or combusted vegetation on the land surface. So it really produces a very unique data set. Just for a little bit of fun to show you that we have been doing this for a while. This was from 15 years ago. And I think a couple people said that we looked like rock stars on an album cover. But here we were flying kind of an older LiDAR system. I think if Chris Bader is in the audience, he'll know this group of people pretty well. But we've been doing this kind of ground and airborne survey for a few years. So our goal is to develop innovative 3-dimensional fuel classification segmentation methods. And that's quite similar to a lot of folks who are doing some really great work out there on fuel classification. And I can name a whole bunch of groups here in Canada who are really leading this kind of work. We're also interested in developing methods to rapidly ingest and output structural attributes, which are important for fire fuel assessment and behavior. This work really is very academic unless we can actually make it operational. So this is something that we're working on. And of course, in doing that, we're also interested in putting our data out there, allowing other people to use it too. So we've been uploading data to the FRDR Federated Data Repository System. We're also interested in understanding how fuels and attributes are changing in the landscape. So not just the technical side of developing these fuel classifications, but also understanding, what are the drivers to these fuel changes and can we understand those? And then also to quantify the post-fire effects. How does this influence how trees are regenerating? What can we expect in the future? So our field data is incredibly important. This is how we basically validate what we're creating from the LiDAR data. And in doing so, we've been installing these the next generation Canadian Forest Fire Danger Rating System fuel plots. And I've got the reference to the field guide as it was produced for June 2023 and led by Jonathan Boucher and his team here. So these folks have been working on this guide for a number of years, and they've kind of brought together the best methods for quantifying fuels in the landscape and for using those fuels within fire behavior models. So as you can see, there's quite a lot of things that are being measured here. We install an 11.3 meter radius plot, and we measure all of the trees within that plot, including the height, the diameter breast height, the species, condition, base of live crown, base of dead crown. We also include a kind of a sub-canopy fuel plot, regeneration plots, soil duff layer plots, and so on. And then we have these long transects here where we measure downwoody debris. So you can imagine that it takes quite a while to measure everything within these plots. On average, it takes us between about 3 and 5 hours to measure within these plots. And often we're measuring, up to 200 to 300 trees. So you can see why we like the idea of using LiDAR to represent what the structural characteristics within these plots. We also collect drone LiDAR and photogrammetric drone data. So we have all 3 of these systems, and this is put together by Saeed Parsian, who's working on the drone data. We have a Mavic Pro, which is a very inexpensive system. I think it's about $3,000, and you can fly it and create these point clouds using photogrammetric methods, which are really very detailed and fantastic to use. However, because they are photogrammetric, if you have a lot of trees within a plot, you're not measuring all aspects of those tree canopies and the understory because of occlusion. We also have a Phantom 4 multispectral system, which we've flown at some plots, but not others. And this measures basically across a number of wavelengths. And so you can tell, discriminate species fairly easily with that. And then finally, we have the Matrice Zenmuse LiDAR system on the Matrice RPAS. And this is a very small LiDAR. It's kind of like, 20 years ago when I was working on LiDARs, I wouldn't have even conceived that this was possible based on the size of airborne LiDARs. But these measure at very, very high resolutions as well, which you can see in the image at the bottom. And with the Matrice, we also have a thermal camera as well, but you have to kind of swap them out. So it has to be, it depends on what we're doing in order to include that. So the goal here is to take our plot data or our plot, kind of the center of our plot, and the plot radius that we measured in the field, as it is very highly accurately located, and to extract all the airborne, this LiDAR data, the structure from motion data, and the RPAS LiDAR from within that plot once it's being kind of slope corrected. So here you can see an example that Saeed produced of the airborne LiDAR data in red and structure from motion data that's colorized. And what you can see here is that the structure from motion and also RPAS LiDAR provide incredibly high resolution or spatial resolution point clouds of the actual structures in the canopy. So if you're used to measuring fuels out in the landscape using those time-consuming plots, which are fantastic and they're kind of like the gold standard, when you get data like this, you start to imagine, maybe I can reduce the amount of time that I'm spending in the field just by flying these systems. But the point is we really want to derive derivative products from those point clouds that we can then compare with our field measurements to determine the accuracy of our methods of deriving those fuel characteristics, and also our ability to kind of scale that up. So here's another example from RPAS that Saeed produced. And if you're interested in this work, we're going to be presenting it in a couple of weeks at the Federal Provincial Mountain Pine Beetle Research Forum that's being hosted by the Foothills Research Institute. So here you can see kind of one single plot of our past data. And then Saeed puts it through a whole bunch of kind of structural filters to quantify the different attributes of that data. And then from those structural attributes, he's able to kind of segment out the foliage, the tree stems, even down to the individual trees, which is quite impressive. He also combines kind of object-based and voxel-based methods for kind of getting into those kind of nitty-gritty parts that are really hard to pull out from remotely sensed data, such as the canopy base height. These are often not very accurately produced in point cloud data because there is a lot of there's a difference between what we're going to measure in the field and our perception of that, where that base height occurs. So just to show you a few results from plots that we collected in Chasmer. So Saeed looked at 8 plots, but he's right now just with structure from motion, but he's adding another, I think 6 to 10 plots using drone-based lidar. But as you can see, his methods of kind of characterizing the attributes and the volumes of those fuels are quite good. So here he produced a scatter plot of the canopy fuel load, and I apologize, I don't have the labels on here, but basically it's the measured canopy fuel load compared with that he's derived from structure from motion on an individual tree basis for all those plots. So that's the benefit of being able to take that plot data and directly compare, the location of the tree that's measured within that plot with the canopy fuel characteristics from that tree as it's taken from the RPAS data. So, of course, we've measured a whole bunch of other things in those plots at which he compared. And through structure from motion, he was able to determine the accuracy of tree heights to a level of about 0.92 to 0.97 R-squared, with RMSE variations between about 0.5 to 1.2 meters. Canopy base height is much more difficult, and correlation was about 0.63 to 0.89, which is actually really good relative to what's out there in the literature. But of course, the RMSE is higher, up to 3 meters, because it depends on what that canopy closure is. If it's really a dense canopy, you're not going to get the penetration of the optical photogrammetric methods into that canopy very well. Canopy fuel load R-squared was 0.73, which is pretty good. And of course, there's additional errors associated with the allometric methods that we're using to determine, what burns within that canopy. Other accuracy or other segmentation of the plots included the coarse woody debris, which he was able to predict where that was to 93% accuracy, and then the species identification, which was up to 98% in those stands. And that's only for 3 species, by the way. So kind of moving into our epic adventure, the first stop for us was Yellowknife. And here's a bunch of us in the truck driving up to, or driving across from Yellowknife to Scotty Creek. A number of us flew, so we didn't all drive up. But as you can see, 8,000 kilometers and 5 people is pretty crowded. We didn't actually measure anything in Yellowknife. We have in the past for a number of years, kind of around Yellowknife. But this year we attended the Canadian Remote Sensing Symposium, in Yellowknife, and a number of students gave talks. This is Linda Flada talking about her work at Scotty Creek and across the Southern Northwest Territories. So from there, we moved on to the Scotty Creek watershed, which, as I mentioned, burned last year. And we measured trees around kind of the northern end of Scotty Creek and around Fort Simpson. And you can see the diversity of trees and forests within that area, all the way from kind of peatlands with trees with stunted growth to quite dense forests with tall trees here. And of course, you can see this is our survey airplane flying right overhead. And when that happens, we get basically laser scanned as well. So we actually look like short trees in the LiDAR data. So when this happens, when we hear the plane coming, we basically move out of the plot as quickly as we can, because that we don't want to add to the amount of biomass within the plot. Another aspect of working at kind of in and around Fort Simpson, which I had to take a photograph of, is the size of the bugs around there. And I think these are I think they're horseflies. I'm not this is an entomologist, but the bugs are huge, and there's lots of them, especially around the little ferry that we take into Fort Simpson at that time. So Scotty Creek is a really interesting, unique landscape. It is found kind of in the southern discontinuous to sporadic permafrost zone. And there are lots of kind of areas of discontinuous permafrost. And I've got a map here on the left, and this is actually laser return intensity from our multispectral LiDAR in green, near infrared, and shortwave infrared wavelengths as this is emitted from our system. And those intensities have been gridded or interpolated across, I think, about a 2-meter resolution. But I've also included kind of underneath this image the hillshade of the digital elevation model so that you can see where the permafrost actually is. And we can identify the permafrost as these kind of upraised, kind of bluey colored areas in that image. And they're blue because the trees on those permafrost plateaus reflect fairly strongly in the green wavelength, which is represented by kind of the blue color gun if you're used to remote sensing. We also see lots of kind of bogs here, which are represented kind of more in the gray to red colors. Those are very wet, often because the permafrost is thawing and the water is basically being maintained within those umbrotrophic or disconnected bog peatlands. And then finally, you have this kind of large channel fen right kind of towards the center left of that image. And that's basically moving water out of that system. And that's highly reflective in the near infrared. And in that area, we have lots of sphagnum mosses, quite a lot of shrubs growing in, because as the water is kind of evacuated out, that fen is drying. And some of the evidence for this, we can see, we published a paper in 2017 on kind of the vegetation height changes and the influence of this thawing permafrost on the vegetation in this area. And basically over time, what we're finding is that the bogs that were previously disconnected and holding a lot of water are starting to become hydrologically connected. So water is moving out of this system. Now, if water is moving out of the system, that indicates that that whole system is drying out, which is a concern for wildfire. Another bit of evidence here that we can see is that, where we've had vegetation height changes in green, this indicates a lot of shrubification of those wet peatland or historically wet peatland areas, which indicates that they're drying out. Whereas in brown, this is where vegetation is kind of dying. And so we expect that these areas are becoming more waterlogged. And so you can kind of see that kind of some alignment between the vegetation height change and the intensity in the different wavelengths on the image on the left, especially where, if you have high reflection of the shortwave infrared, that indicates kind of a drying of the environment. You'd have more absorption if you had, if it was really, really wet. And kind of a correspondence with the growth of vegetation in that area. So this is an issue for fire because we're seeing these landscapes changing quite quickly. The trees are dying, peatlands are drying out, and fires can move into this area. And of course, that's exactly what happened in September of 2022. So in September, about half of the watershed burned with a very severe fire. And I plotted this difference normalized burn ratio from Landsat overlaid on top of the hillshade of the digital elevation model for Scotty Creek. And you can see the fen here in this kind of that green channel fen that's kind of drying out. In this image, you can see that the normalized difference burn ratio indicates the highest burn severity in areas where that fen is evacuating water, is moving water out of that system. If we compare that with a land surface classification, which I did previously with LIDAR and high resolution optical imagery, we can see that kind of the areas with the most severe fire are within the fen and the upland areas, where of course bogs tend not to burn quite so severely because they remain waterlogged in that landscape. So they're basically like impeding the movement of fire, and you can see that in the image as well. Okay, so that's why we're measuring a lot of the forests in this landscape, is because we want to get a better sense of how these ecosystems are changing, what is kind of causing fire to move through those systems, and what is kind of impeding fire as that permafrost thaws. So the next place we went to is Watson Lake, and we collaborated with Yukon Wildfire there, who were doing some prescribed burns up near Whitehorse, so we surveyed that area as well, but my group didn't actually measure that. We just measured a few plots in and around Watson Lake in areas where we previously collected LIDAR data in, I think it was about 2008. So here you can see Italo is, he's from Brazil, and for him, this was a real experience. He was just absolutely fantastic in the field. And you can see him hugging the tree kind of on the bottom left. And, here's our drone system. So we typically fly drone before we do the measurements, because we want to make sure that we haven't trampled that ground surface or the vegetation, and have that be represented in the point cloud. So by the time we got to Watson Lake, and it really wasn't very long into our field experience, we found that there's just so many trees to measure, and it just takes forever to do these plots. Not to put the plots down, we still really, really need them. But we were kind of thinking of all kinds of ways that we could make this faster. And so we were still measuring our plots. We're still putting in, within a drone survey area of about a hectare, we were still including 2 next-gen CFFDRS fuel plots that had everything measured within them, but we'd also add a third kind of what we call an RPAS quick plot. And with this, basically, we're using kind of our methods to characterize those trees, but we're also just measuring only 10 trees and locating them within the plot, as well as the more difficult things to measure that maybe RPAS isn't so good at, like, downwoody debris, the duff layer, the upper story, and so on. So in doing this, we were able to reduce the time of measurement from about 3 to 5 hours for a single plot to about an hour, which is really impressive. And we kind of thought this was just absolutely fantastic because we're getting more plots, but they're kind of in addition to what we're collecting. So moving along, we were very fortunate to miss a lot of the fires that occurred this summer because we were kind of early in the season. We did a lot of this in June and through July, but we did see a number of fires as we were driving, which you can see here, and some of them, I think, as we were driving through northern BC, some of those fires contributed to some of the big fires that we saw in the media, and you can see them here. Now, driving through BC, northern BC, I don't know if you've ever done it, but there are some incredibly beautiful places out there. We stopped in kind of in this village here where, people fly in and out with a float plane, and they have all these beautiful little cabins. Lots of bison kind of along the side of the road. And this bear was kind of interesting. We stopped in at a gas station to get some food for the road. And there was a couple of conservation officers there just chatting with the shopkeeper. And of course, I think, I don't know, a couple of us wanted, not me, but a couple of people wanted to get kind of selfies with the conservation officers. Didn't, it's kind of embarrassing. But as we walked back to our truck, we had this bear basically following us, and we didn't even know. He just kind of came right up behind us, and we got in the truck, and as we got in, we saw him right there. So that was our close encounter with a bear. But it really wasn't too bad. And of course, when you have so many people in the field making lots of noise, we've been quite lucky with regards to not seeing too much wildlife in our plots. So we continued to drive down to Chasmer. It's quite a long drive from Watson Lake to Chasmer, and we saw more forests that had been burned in the recent past, some really severe fires. Here you can see bottom left, this forest recovering, but the trees are really basically completely decimated. But we thought it was really interesting how these forests were recovering. And then finally, we got to Chasmer, and we've been working with Raphael Chevardez and Chris Watson a little bit on the Chetamon fire. And so we went into that kind of burned area that was burned by the Chetamon fire in last year. And what's interesting is that this was a really severe fire, and you can see that the fire actually burned some of the mosses underground. And there were huge kind of Douglas fir trees that were completely burned up. It was really quite amazing. But what we're interested in is basically looking at the fire history in this area. And we were lucky to collect or have LIDAR data collected by Parks Canada before the fire. And of course, we collected LIDAR data again after the fire. So what we're interested in here is basically looking at kind of the burn severity across that burned area and the fire history. So Raphael and Lori Daniels have a whole bunch of plots in here that have kind of a paleo fire history within this forest. So what we did is we went back into all of those plots and we took photographs, and we basically measured a composite burn index for each of those that we can compare with the loss of biomass from the LIDAR data, the calculation of a burn severity index from the multispectral parts of that LIDAR data that's produced. And we can start to see, does paleo history or return interval influence how the burn severity in this area. So this is my one little tiny part of kind of the hero aspect of my story. And it was really interesting because as we were working in this forest, we came upon this young man who was actually trying to die by suicide. And we managed to, talk to him and kind of convinced him, or I think he probably was convinced himself that maybe that wasn't such a good idea. And a couple of the members drove him onto the hospital, but he also tried to kind of stay out overnight, and he started a small fire in the forest in the area that hadn't burned, and that fire started to spread into kind of the surrounding area and into the trees. And so if you look at this photograph, you can kind of see where that fire was that he started. And of course, we were lucky because we had kind of inReach, and we kind of radioed it into Parks Canada, and they came out and put it out, and he also had a motorcycle back there and took his motorcycle out. So I think overall that was a really happy ending. But compared to what firefighters go through, this is absolutely nothing. But for us, it was a pretty big deal. So in Chasmer, kind of continuing on with the measurement of fuel plots, we put a whole bunch of fuel plots in here. All of this is supported by Canada Wildfire, and in this case, we had a lot of support from Foothills Research Institute and MITAX. But we're really interested in seeing how the fuels vary with mountain pine beetle phases, and you can see this forest that's being decimated by mountain pine beetle. It is basically this red to gray phase, but there's a lot of new understory growth, which is really interesting. So you have the combination of these dry fuels in the canopy that are really highly flammable, and the latter fuels combined with the uncertainty of these regenerating saplings growing in. And so we're really not sure how fire is going to behave if a fire actually occurs in this area. So that's something that Foothills Research Institute have been really, really interested in. So this kind of moves us into, sorry, I'm going to kind of back up there, using airborne lidar for understanding the structure of those fuels in the environment. And this curve basically represents kind of the mean structure in the frequency of the number of laser pulse returns with height through the canopy. So you can kind of map these out. Basically, you're counting them after you normalize for the elevation at every kind of 1 meter up into the canopy. It's a very simple method for characterizing kind of the biomass in that system. Basically, the idea is that if you get a laser pulse reflection in the canopy, there must be something there that caused that reflection to occur, like, a branch or something like that. The kind of the light green area represents kind of the variations in those plots. So we extracted, basically 20 kind of lidar-based plots. These are not measurement plots, but lidar-based kind of plots of those structures. And what's also interesting is that lidar provides an opportunity to measure a lot more of the structure than what we can actually measure in the field, where we're just basically measuring the top of the canopy height, the top of the tree height, and the base of the canopy. So this is what the distribution of the returns looks like at the kind of green phase or for healthy trees. Now, as you kind of go through the phases of attack, This is the early red phase. So this is as the trees are turning, they've been infected by mountain pine beetle. They're using their sap to push the mountain pine beetle out, and the tree is basically dying. So the needles turn red. And you can see here in the distribution that we're starting to see kind of more accumulation of biomass. Sorry, this is kind of advancing, I didn't realize. More accumulation of biomass lower down in the canopy, as represented by those point clouds. As we go to the late red phase here, just a few needles remaining on that tree, on those trees. A lot of the branches are starting to break down, and so we get the accumulation kind of more kind of shifted down in the canopy, much more kind of ladder fuels. Finally, gray phase, the tree is fully dead. No needles in that canopy, and the ladder fuels are basically kind of shifted down to the ground. And then finally, you get this kind of late gray phase with regeneration. Trees are falling over. A lot of that fuel is accumulated as coarse or downwoody debris in the understory, and then you get some regeneration as well. So this is a really good, simple method for understanding the distribution of the biomass within those canopies. Now, with multispectral LiDAR, we can also see how the structures vary, as well as kind of the reflection of the intensity of the different wavelengths. So on the left, we have this kind of composite image of the shortwave infrared, near infrared, and green wavelengths in these kind of three different colors or color guns, often used in kind of old remote sensing terminology. And you can see kind of areas where, you know, there's some mountain pine beetle impact. But if we look at the near infrared intensity and the shortwave infrared intensity, near infrared represents, if you get areas of high reflection, healthy vegetation that's slightly moderated by the structure and the scattering properties of the pine needles. Shortwave infrared indicates areas that are kind of either burnt, which we don't see in this area, but also areas that are drying. So anywhere where you have a high reflectance of shortwave infrared indicates kind of a dry area. And this could, you know, is also important within those kind of dry, dying trees as well. So using fairly simple methods, we can basically look at the point cloud statistics of the distribution of those point clouds. So here we're looking at basically, you know, at the bottom, some of those LiDAR statistical derivatives, very simple to implement in LAST tools or LiDAR. You know, we're looking at, you know, what is the 95th percentile of the height, or the, you know, 95% of the returns are within a certain height. Or we can look at the standard deviation of the heights. We can also look at the interquartile range, which is the distribution between the 25th and 75th percentile, which is highly correlated to canopy biomass. And then we can compare those basically using a simple regression with all the measurements that we did in the field. And we can figure out kind of, you know, what derivatives compare best with what plot measurements. And so in the red, you can see strong positive correlations in some of those statistics, those point cloud statistics, like, you know, the standard deviation of the returns within that plot are highly correlated with the standard deviation of the dead canopy base height, and so on. So very simple, lots of people have used these kind of methods, but we can also incorporate some of the intensity attributes as well. Here, you know, we have kind of near infrared intensity, high, strong negative correlation with like the canopy base height and so on. So if we put these together, and create kind of a multiple regression, we can use that as a simple model for canopy fuel load. And so we were able to predict this to an R squared of about 0.93 when we compare that with our allometrically derived fuel measurements within the field. And these are basically on a plot extracted basis. And, you know, based on that multiple regression, we can create these fairly simple fuel maps for Chasmer. Here you've got like whole tree biomass and the spectrally adjusted canopy fuel load. So spectrally adjusted meaning that, you know, we have higher preference for potential flammability based on the drying potential of those trees. So kind of to wrap up, we continue to collect more plot data and drone data at Waterton and along the Bow Valley where we had collected LiDAR data in the past. And overall, you know, over the last, oh my gosh, it's been 21 years, we've collected almost 200 biomass and fuel plots that we have coincident with airborne LiDAR, and some of those with terrestrial laser scanning and RPAS. So our idea is that we really want to create these kind of more sophisticated derivatives using 3D object-based segmentation methods and deep learning using artificial intelligence. So here's just kind of one example of where we're going with this. We published this last week. Actually, Zhou was a postdoc with us. Now he works as a scientist at Canadian Forest Service. So super happy. He's just absolutely brilliant on delineating and reconstructing 3D forest fuel components and volumes using terrestrial laser scanning. And here you can see that, you know, he's basically recreating these point clouds as three-dimensional object kind of primitives. So these make the calculations even more, it's basically like a direct calculation of that volume. So what's in our future? I mentioned at the beginning that we're really interested in using this plots and the LiDAR data for operational fuel management. And we collaborated with Hatfield to basically create this rapid tool for ingestion of LiDAR data and production of canopy fuel metrics and forest structure metrics. So if you're interested, Hatfield have produced this fantastic story map. I think you could probably just do a search on it. It's called ArboSense, and they go through and show you how these spatially explicit attributes are determined. Now, this is kind of the first step. They've only ingested the montane ecosystem plots that we've collected, but in the future, what we're hoping to do is make this a whole lot better by including all of our plots right across Western Canada and making these methods a lot more sophisticated. So that's kind of coming up in the next couple of years. But basically what it means is that you could just upload your data or grab the tool, upload the data to the tool, process the data, and it'll basically output these fantastic maps. And then you can go in there and figure out, you know, where the canopy bulk density is really high, you know, where's the ladder fuels exist within this landscape, and how do we go in there and manage those fuels. So that's all for my presentation, and thank you very much for joining me, and I'd be happy to take any questions.
Thank you, Laura. That was really great. It sounds like an awesome, or I guess epic field season for you and the students on so many levels. And I appreciate you sharing some of those little tidbits about things that aren't necessarily captured in the science to speak, because it brings it down to real life, which is nice. So thank you for that. We have one question in already. So this is from Chris. Hey, Laura, great presentation. The field protocols were not necessarily developed with remote sensing in mind. Did you have to make any adjustments to the protocols to better link your ground plot data to your remote sensing data?
Yeah, and Chris, that's a great comment, and I really appreciate that. We're always kind of looking at ways to kind of match everything. And I think probably the one thing that we thought was really important is that, measuring all trees is really time consuming. And if you don't need to measure them all, like if you don't need them for fire behavior models or whatever, it really depends on what your goal is, kind of the end game for what you're doing. But for us, we found that measuring all trees was imperative, because in these natural landscapes, tree height and structure variability is highly variable. So it's not necessarily represented by, just measuring a few trees. However, in our quick plots, we did measure kind of a few trees, but the goal is to match that with the RPAS and kind of fill in the gaps.
Thank you. The next question is related to Chris's previous question. So this person's also curious about the same question. They previously had issues using surface fuel data that was collected over linear transects to correlate to LiDAR metrics that were derived from plot level metrics. It's not really a question there, but if you have any comments on that.
Yeah, again, I think it depends on, the method that you employ. We've used a lot of linear transects as well, with kind of small plots. And what we found is that, if you're using kind of small plots along linear transects with LiDAR, airborne LiDAR data, often you don't get enough point returns within those small plots. So, that's something to consider. Meter size plots, maybe not enough returns, but if you extend to like 2 by 2 meter plots, it can be a little easier. And of course, you're also kind of saying, well, this tree is located right here on this transect. Am I seeing it in the LiDAR data? And you just may not have enough reflections to represent that tree. So I think that, for this kind of work, mensuration, like these large plots, are kind of the way to go. Or, if you have a lot of trees, there could be the potential for making plots a little bit smaller, like half the size, because really, I think with these, 400 meter square plots, you're trying to capture the, like a statistically significant number of trees within that plot to represent those characteristics. Clearly, if you're measuring like an oak forest with big, huge trees, you want a big plot. Maybe there might be the potential for measuring small plots, but of course, I'm this would need to be looked into thoroughly.
Thank you. And thank you to Eleanor for posting the link to the story map. Some people are asking for that, so thank you very much. Okay, I see. On a similar vein, the new generation CFFDRS has a pretty specific protocol for terrestrial LiDAR. Did you follow that protocol exactly, or did you have to modify it and do more or less scans? What about the LiDAR target location?
Yeah, terrestrial laser scanning is awesome. We've been kind of working on TLS basically since the very first terrestrial laser scanner was like the prototype one we worked on in 2002. Chris and I together did that. And so we really experimented with the positioning of the scanner and the targets. And we really tried to follow closely what the next gen CFFDRS methods were. But sometimes, you've got this big shrub in the middle and you kind of have to adjust because you're going to get a lot of occlusion. We become very good at tying shrubs down so that we can scan beyond. But sometimes, you need more scans. So what we typically do is we scan kind of from outside of the plot in, and we align with those targets. But we also have a scan in the center that kind of is a full kind of rotating 360 scan. Jojin, she is really expert at this kind of thing. The other aspect to TLS is that it takes a lot of data cleaning, and that takes a lot of time because you get basically split returns, which create what are called ghost points, basically returns that are kind of like it's almost like a mirage of something else that isn't actually reflecting from any biomass or any part of the tree or vegetation. So those all need to be cleaned up. So you've got kind of alignment, and then you've got the cleaning of those points, and that can take quite a while.
Thank you. Dr. Hopkinson's chiming in on the chat as well, saying that yes, the stem ID location, or at least a sampling of some tree locations, was needed for our pause, assuming this is calculation validation, at the tree stem level, given we are now extracting and mapping fuel metrics at stem level. This dramatically increases N for model significance.
Yeah, absolutely. You know, it's you know, we've been kind of looking at this for quite a while, and Chris is a lot more expert at this than I am, as is Jojin. So yeah.
Okay, we have another question here. What do you foresee as the applications for this research for measurement or remeasurement in areas of recent burn, especially mixed severity fire? From a wildfire management perspective, I would be interested in how this could apply to predicting when an old burn scar would become receptive to fire again.
Yeah, that's a really interesting question, because what we found is that, you know, you can kind of measure some of those burn stems, but what's really interesting is that, you know, we can measure the post-fire regeneration of those canopies. And in fact, Chris and I have supervised a couple of students at Waterton looking at that post-fire regeneration, basically the rates of growth in the early period following fire. And, you know, initially, the separation between the canopy or the vegetation on the ground, you know, when you fly it basically right after the fire, you can get a good ground elevation. And then, you know, as you kind of repeat fly these areas, you really need to use that kind of original ground elevation to normalize the height of that vegetation, the biomass. But basically you get, you know, really, really dense vegetation kind of in the early years. As vegetation kind of grows up and you start to get the differentiation between trees and shrubs and herbaceous, you start to kind of see that separation. Of course, we need to do more work on that. It's kind of an evolving field. But, you know, I had a student, Humera and Ayatullah, who kind of looked at a burn chronos sequence over time and started to be able to differentiate, you know, younger, recently burned vegetation regeneration versus older burn vegetation regeneration. So I think there's a lot of potential to develop that.
Yeah, and I would imagine it would have a lot to do with what species you're regenerating with in your successional stages. I know often we think that we have this burn return interval, and then depending on what's there, it can return quite quickly, even in something like a young pine stand. So I have a question. You mentioned a couple times about the future and looking to making this operational or operationalizing the use of LiDAR. And I was curious, when you're using that term, are you referring to people in the field? So perhaps like a fire smart assessment crew having access to their own LiDAR devices and then having access to a tool like you did through Hatfield where they can then plug it in? Is that the intention there?
Yeah, I think so. Like, you know, with structure from motion and kind of the drone-based LiDAR, there's lots of potential for, you know, groups having these fairly inexpensive systems. You know, the Mavic, you know, is around $3,000. Of course, you need the software also to process that, which is a bit more expensive. But you know, a lot of this data can just be uploaded to the cloud and automatically processed. And then, there's also a lot of LiDAR surveys that are already out there that, folks are putting online. I know like our group, and of course I work really close with Chris and, Chris's group. They're, putting data online as well. So, it's, I think there's a lot of potential for groups to use already available LiDAR data. There's provincial LiDAR data sets to kind of understand and map those fuels in the environment. But it's also important to recognize that this is a snapshot in time. And so those fuels change. So that, bringing those drone-based LiDAR systems in, could potentially help to add more sampling to those areas for, for example, for fire smart, or fire management around communities and that sort of thing.
Great. Yeah, it's a snapshot in time, but when you get this series of images or scans over an area over time, you get some great information about change as well, right? And the reason I was asking specifically about, for example, like a fire smart assessment is I have family that works, they're arborists, and they do work for counties on tree removal. And I know they're always looking for ways at that level to be able to quantify what they've done. And then also something as simple as I think of training as well. So I was out on one of the sites and I'm looking around. Great job, you guys. You fell and you pruned and you did all this, but everything that you did is now laying elevated on the surface. You have no ground contact. And so you've essentially created all of these low-lying fuels that are going to dry out. And so I just kind of wonder in a way if it couldn't almost be used as a quality control metric in some ways in situations like that.
Yeah, absolutely. I mean, there's a lot of, potential for basically, like we have these piles or this, there's this added risk, and I think, we're not quite there yet, but I know that there's a lot of LiDAR folks out there who'd love to see their LiDAR data used to parameterize some of the fire behavior models. So that's another aspect of this, you're getting kind of this range of variability that you wouldn't necessarily get in, with fuel plots. So you can it's almost like, an ensemble approach to modeling. You can see how things are changing in the landscape, but of course we're still a little ways off, but I know that, folks, the modeling community are kind of moving in that direction. I think that's a really positive step. We've got another student in the group, Tristan Skredding, who is doing some really neat work, kind of comparing, kind of the timing of fire, like the fuel management and kind of removal, and how over time those fuels are changing and growing back, and when do you have to go back and manage that area again? Because 19 years ago when that area was managed, or maybe 16 years ago, may not be good enough anymore, and so there may be kind of a false sense of security as well.
Oh, that's great to hear. I think that's a big question, operational fire management as well, is when do we reclassify our non-fuel cells as fuel, whether they be previous burns or things like that. So it's nice to hear that research is coming out. So I don't see any more questions in the chat. We can give it a minute here for if anyone has anything else they would like to ask. And just to remind everyone, this has been recorded. It will be uploaded onto our YouTube channel sometime next week. I posted in the chat as well a little bit about our upcoming webinars. So we'll have a basic introduction to modeling in November, and then we'll have Chris Stockdale talking to us about Burn P3 Plus and some of the great stuff that's going on in that model in December. And in January, we're going to have a look back at the 2023 fire season. So we've got some great presentations lined up for the next few months. I've also included a link to read more about those presentations, as well as our subscribe button, so that you can receive notifications about upcoming webinars and such. So I don't see any more questions. Laura, do you have any last comments you'd like to make before we close down?
No, well, just, to thank Canada Wildfire for the support. They've been really instrumental in helping us collect all of these data sets. So that's been fantastic. Of course, NSERC and Foothills Research Institute as well, and Hatfield, and all the great folks that were involved. And, Chris Hopkinson, who manages the lidar system as well. So that's it for me.
Awesome. Well, thank you so much for taking the time to join us today and sharing this awesome field season. And to everyone, I hope to see you in November. Have a great weekend, everybody.